Hello friends, welcome to Electronic Circuit Hub. So today we are gonna understand about the design and simulation of three-phase full bridge converter. So I'll explain how you're gonna design your three-phase full bridge converter, and then later I'll run the simulation and I'll show you the different voltage and current waveforms at different nodes. So this is going to be very interesting video for at least me. So let us start with the requirement. Let us start with the input and output specification. Okay, so the input is 230 volt RMS and 50 hertz, and the output is 8 volt 10 amps. So I want to design a full bridge converter with the having input of 230 volt RMS with 50 hertz frequency, and the output voltage is 8 volt and 10 amps. So basically this is our requirement to design a three-phase full bridge converter. Okay, and now let me explain you the different block of this circuit so that you can understand. So let me start with the input. So as I said, our input is 230 volt VRMS and 50 hertz, and since we are designing the three-phase system, so we'll have the three power source here. Okay, so if you look at here, this is L1 and this is L2 and this is L3, and if I right click on this sources, okay, so if you look at here, the amplitude of your L3 power source is 324 volt and the frequency is 50 hertz. So what I'm doing here is, since your input RMS is 230 volt and LTspice don't understand the RMS, so you have to give the peak voltage here in order to understand the LTspice. Okay, so 230, if you multiply by 230 into square root of 2, you're gonna get 324 volt. So this is basically the L3, and let's say L2. Let me right click on here, and the L2 is again 324 volt 50 hertz, and the phase difference between L3 and L2 is 120 degree. So make sure that if you are creating your three-phase system in LTspice, you have to also give the you have to also define the phase degree of your input source. Okay, so for this L2, my phase angle is 120, and if I right click on L1, if I right click on L1, you see here the amplitude again is 324 and the frequency is 50 hertz and the phase again is 240. So for L2, for L3 we have 0 phase degree, for L2 we have 120 degree phase, 120 degree, and for L3 we have the 240 degree phase angle. Okay, so this is basically your three-phase power input power source. And if you look at here this point, so in order to, since this is the peak voltage, our AC voltage, AC RMS voltage, in order to convert it into the DC voltage, you need to use the full bridge rectifier. So this is the full bridge rectifier. You see D5, D7 and D8. These are the full bridge rectifier. Since we are using three-phase system, so that is why you have to use the 6 diode to convert the three-phase input to a pulsating DC. Okay, now at this point you will get your pulsating DC, and in order to reduce the ripple voltage and smoothen your pulsating DC, I am using here a bulk capacitor, raw DC capacitor, which convert a pulsating DC to smooth DC. And here you see this is the 100 microfarad. And if you talk about the diodes here used for AC to DC rectification is MUR460. And if you further move this side, if you further move to after the rectification, and after this bulk diode we will have the 4 MOSFET. Okay, so if you go and look at the configuration of full bridge converter, it is having your full bridge converter is having the 4 bridge 4 MOSFET in order to drive your primary winding of your transformer. Okay, so if you look at M1, M2, M3 and M4 and how these MOSFETs are working. Okay, this is very important to understand how these MOSFETs are working. So MOSFET M1 and M4 are turned on together. So MOSFET M1 and M4 are on together, turned on together. So we have to apply the same driving signal for MOSFET M1 and the same driving signal for the MOSFET M4. So the current path is, once your MOSFET M1 is turned on, so it's from high voltage DC to M1, then it goes to the transformer, and then again it goes to the MOSFET M4. So you have to turn on both MOSFET M1 and M4 together, and then for this MOSFET M3 and M2. So how you gonna do this for MOSFET M3 to M2? So once MOSFET M3 is on, okay, so if you look at this VP2 point, there is a current flow in the primary winding of your transformer again, and what happens here, it comes here, and at the same time, since your MOSFET M2 is turned on, it is completing the ground path. So from high voltage DC to M3 to M3 to transformer, and then it goes to again M2 to ground, and that is how your M3 and M3 this MOSFET and this MOSFET completes the path. Okay, and one more thing you have to remember here is since your MOSFET M1 and M4 are turning on together and MOSFET M2 and M3 are turning on together, you have to make sure to define the dead time between MOSFET M1 and MOSFET M3 turning on. So once MOSFET M1 is turned on, at the same time MOSFET M3 cannot turn on, only the MOSFET M4 can turn on, and for this pair, for M3 to M2 pair, between the turn off of your M1 to M4 and the turn on of your M3 to M4, you should define a dead time, otherwise your switching is going to short with directly, probably with the VCC, and it is going to damage, right? So then if you move further in your circuit, so this is the primary winding of the transformer L3. The inductance is 1150 microhenry, and if you look at the MOSFET, 4 n channel MOSFET, all 4 MOSFET are the same, and it is STP8NM60. And then if you look at the secondary side of your full bridge converter, and if you look at L9 and L10, the inductance value is 900 microhenry, and for both L9 and L10. And if you look at here, I have defined the coupling factor between L8, L9 and L10. So coupling factor denotes K. L8, the coupling between L8 to L9, and the coupling between L8 to L10, and which is 1. So in practical, your coupling factor cannot be 1, it should be less than 1, but for the sake of simulation right now, I am using the coupling factor which is 1. And if you talk about the secondary side now, okay, the two winding of your secondary winding of your transformer Ln and L10, then you have 2 diodes for rectification of your secondary voltage, both diode. And if you look at output of this diode D9, and output of this diode D1 is shorted to. What does it means? That the cathode of your D1 and D9 are shorted together, and the output of your D1 and D9 goes to the inductor here, and this inductor value is 330 microhenry, and this inductor and this with this capacitor, okay, with capacitor C4 forms a low pass filter, and it always allowed to pass the low frequency components of your full bridge converter. Okay, then this also gives the transient supply to your load, and for this simulation the load is 100 milliohm. And if you talk about the driving, how you gonna drive your MOSFET M1 and M4 and M3 and M2, this is also important to understand how you're gonna do this using LTspice. So if I go the MOSFET driving section, this I can define this as a MOSFET gate driver. MOSFET gate driver. Okay, MOSFET probably gate driver. So you can define this as a MOSFET gate driver, and this section is your MOSFET gate driver, and you can draw the line here. Okay, because this is your MOSFET gate driver. This is your MOSFET gate driver, right? And this is your input power source. Input, let me do this, let me define this for you. This is your input, so you can define this also. This is your input supply, supply. This is your input supply. So again I write this input supply. Then here you have your rectifier and three-phase rectifier, and let me do this for three-phase rectifier and the capacitor. So this is your three-phase rectifier, right? This is your three-phase rectifier, three-phase rectifier. Okay, this is your three-phase rectifier. So I'll put here and the three-phase rectifier probably, and filter, and then you have here the MOSFET, the 4 MOSFET, and then you have the secondary. This is your primary side of the transformer, and this is your secondary type. Okay, so you can do like this. This is your transformer, these two are the transformer, and this the secondary side again. So I was talking about the how you're gonna define the MOSFET gate driver. Okay, so if you look at MOSFET gate driver, we this L4, L5, L6 and L7, and the L4 is connected VP2 and VG2, and VP2 and VG2, VP2 and the VG2. How it is defined? This is L4 is VG3 and VP2. VG3, this is your VG3 and this is your VP2. So this is L4 is the MOSFET gate driver of M3, and then L5 is VG4 to ground, L5 is for M4 VG4 to ground, and then L6 is VG2 ground, so L6 is for M2, and then L7 is VG1 to VP1, that means M1, VG1 to VP1. Okay, so guys, hope you understood how you gonna construct the three-phase full bridge converter in LTspice. And now I'm gonna run the simulation and I'll show you the different waveforms so that you can understand the behavior of this circuit, this critical circuit, how you're gonna design and how you're gonna simulate in your LTspice. Okay, so in order to run the simulation, go at simulate button. So go at simulate and then edit simulation command. I am already using the stop time is 200 millisecond, so I straight away run the simulation. So I'll go here the simulation, then I'll go here and I'll go tile window vertically. So this is okay, maybe zoom fit if it is happening. Now the first thing, let me show you the the gate driver signal. Okay, let me show you, start from the input. Why I want to show you the gate driver? Okay, let me start from your input. So this is your L3 signal, and this is your L2. Okay, and this is your L1. Okay, so this is the input signal of your power supply, and since you are using the three-phase system, you can see here there is a phase difference between different between L1, L2 and L3, L3, L2 and L1. So this is basically your input source, and if you add the plot pane here, you can see your rectified DC. Okay, so you can see here, this is your input source, and this is your rectified DC. Rectified DC means I am checking my signal here at C across the C3, and this is also called not only the rectified DC, also it is called the pulsating DC, or it is also called the raw DC value. Okay, and this is high voltage. If you look at here, my raw DC voltage is how much? If I look at the peak, it is 560. Okay, and if you look at the down, it is 538. That means more or less I have 20 or 22 volt ripple across the C3 capacitor. If you look at here, now the most important thing which I wanted to show you guys is to show you the different gate driver signal. Okay, so in order to show the different gate driver signal, let me show you the first the signal between VG1 to VP1. Okay, the signal between VG1 to VP1. In order to do that, let me delete this. Okay, let me delete, so that you see the signal between VG1 to VP1. Okay, and the signal between VG1 to VP1. Okay, so this is basically the signal between VG1 to VP1, and let me show you the signal, because I said MOSFET M1 and M4 are on together. Let me show you the voltage across VG4. Okay, so this is voltage across VG4 and the VG1 and the VG1 and the VG4. And if you look at here, we have the clearly, let me delete this not needed, right? So let me delete this, a little bit confusing for me this as well. So let me show you the voltage across VG4. So this is your voltage across VG4, and now let me show you the voltage between VG1 and VP1. So the both the gate driver signal for M1 and M4. Let me click here. Let's see how this you can see. So if I zoom this both waveform, you can see here very clearly that your both the gate to source voltage of VG4 and the gate to source voltage of VG1. That means both MOSFET M1 and M4 having the same amplitude gate driving signal with the same, I would say, same frequency. If you drag one thing is here, now you can see clearly what you can see here. Your VG1 and VP1 are in the same phase and in the same polarity with the same amplitude. Now I'm gonna show you the voltage across this VG3 and VP2. So, and here let me show you the voltage across VG4. Okay, and if you look at here, the voltage across VG4. Okay, and voltage across VG4 and the VG2 as well. Okay, so let me zoom now how it looks like. Okay, now I'm probing all my 4 signal. Okay, let me show you guys all my 4 signal how it looks like. Okay, it's important to understand and look. Now you see the VG1 and VP1 is the MOSFET M1 driving signal, and the VG3 and VP2 is MOSFET M3 driving signal. And if you look at here, both MOSFET M1 and M3 is having the driving signal of the same amplitude opposite polarity. And if you look at here, there is some dead time. If you look at here, there is a gap between MOSFET M1 gate driving signal and the MOSFET M3 gate driving signal, and this gap, if you look at clearly here, this gap is called the dead time. And in order to drive the full bridge configuration, you have to give some dead time, otherwise your signal is, your MOSFET gets shorted together. So there is a dead time between the complementary MOSFET driving signal. So I said M1 and M4 are turned on together and M2 and M3 are turned on together. So between M1 and M3 or M2 and M4, there is a dead time, and that's what you can see here. That's what you can see here. There is a dead time. There is a gap between the driving signal of the complementary MOSFET. Okay, there is always a dead time. Okay, so this is about the dead time. And if you look at the voltage across the MOSFET, let me show you the voltage signal right now. This is very important again to check what is the voltage appears across your MOSFET in the full bridge rectifier. Can you see, guys? This is the voltage across the MOSFET drain to source, and if you look at here, it is the peak voltage is 550. Okay, this is 550, and low side, if you look at here, this is 0 volt. And if you go and compare, if you go and see any full bridge MOSFET drain to source signal, it looks like this. Okay, it looks like this. You can understand little bit of theory, but it looks like this. And now I'm gonna show you the current across the primary winding of the transformer, and this is the current across the primary winding of the transformer. Okay, the current across the primary winding of your transformer IL8. So if I divide into the plot pane and I put here, and if you look at now, this is your current across the primary winding of your transformer. Okay, this is current across the primary winding of the transformer. If you look at the voltage across your primary winding, let's see how it looks like. The voltage across the primary winding, let me delete this, let me delete also this. Okay, so this is your voltage across your primary winding of the transformer. Okay, now if you look at the secondary side, let me show you what is happening at the secondary side. Okay, so at this node, let me show you the voltage, how it looks like. Okay, so let me delete this. At this node, you can see the voltage looks like this at this node. And if you want to check the voltage of the secondary side, let me show you. So let me delete for the now, and let me show you other winding voltage as well. Okay, can you see? So now you can see this, that is how your voltage across the secondary winding looks like. You can also see the current across the secondary winding. This is the current across, let me delete this, the secondary winding. That is how it looks like. And this is also the current across the secondary winding. That is how it looks like. If you look at here, both current are in the opposite phase. Okay, when this is 0, this is high current. When this is high, this is going to 0. So you can see the current across the secondary winding of your transformer in full bridge converter. Okay, if you want to check the diode current, you can check. That's not an issue. You can check the diode current. Okay, let me show you the diode current, and let me show you the diode current for D1. So you can see the diode current for both. Let me delete this, the inductor current, the transformer current, and this is your diode current. Okay, from 0 to 10 ampere. Okay, and again from 0 to 10 ampere. And let me show you the inductor voltage now, inductor current, the secondary low pass inductor current. And that is how, let me delete this at the moment, diode current. So that is how your inductor current looks like. Okay, this is your inductor current of your full bridge converter. You can zoom in, it looks like this, inductor current of full bridge converter. Okay, it's working in the continuous conduction mode. Okay, this continuous conduction mode, it looks like this, it looks like this is working in the continuous conduction mode. And now finally, let me show you the output voltage. Okay, So this is going to be our output voltage. Oh, let me delete the current now. So this is you're going to your output voltage, this is you're going to the output current, and let me add some plot pin here. So this is output voltage, this is output current. Let me change the color here, this is red. Let me change the color for this as well, this could be this. And now let me show you the power, finally power of your full bridge converter. Okay, so this is your power of full bridge converter. So if you look at your output is around 8 volt. The current is 100 sorry, the current is 10 ampere. The current is 10 ampere, and if you look at the power is more or less 80 watt. Okay, 80 watt if you look at here. So guys, I hope that now you are able to understand what is full bridge converter, how you gonna design the full bridge converter in LTspice. Okay, how you select the different components, how you see the voltage and the current waveform at different node, the way I have shown you in the simulation. If you have still doubt on this circuit, feel free to ask me in comment section. Thanks for watching this video.